what we build. Perry Parts specializes in tuned dampers, 3D printed out of elastomers. We manufacture, kind of our bread and butter product is a elastomer bump stop for a lot of off-road vehicles and race applications. And the real benefit by leveraging 3D printing in this application is the tunability, the ability to modulate density of the part so that way you can create different internal structures and different compression dynamics on vehicle. So you could make something stiffer, softer. You can make the spring rate curve more or less progressive. You can even do some really crazy stuff with buckling structures, so that way your initial engagement is firm, but then the part compresses more easily after you get past a breakaway point. So that's kind of our niche. But one of the other really cool things by being 3D printed, by making a 3D printed product, apart from all the permeability or permutations that you can create, is the ability to bake in geometry that's otherwise not possible. So our parts aren't just a regular rubber spring like a lot of traditional bump stops are. They're actually a damper. So in the same way that a spring is to a rubber spring, a damper this equates much more closely to a shock absorber. So by controlling the airflow in and out of ports on the bottom of the part, you're actually able to shed a lot of that kinematic energy of contact through turning it into heat. So the resistance of pushing air in and out of those ports helps you dissipate some of that energy, turn it into heat, and actually control the vehicle's ride. Going back to this slide really quick, for those of you who don't know what a bump stop is, it's this part right here that sits in your suspension. And as your control arms or your axle moves upward, the bump stop actually engages and catches that to provide a final suspension stop. These parts are engaged much more frequently than a lot of people think, and the goal here is to create a near bottomless feel. So you want it to be soft on initial contact, ramping up to a ultimate stop, and along that whole progression curve, you want to shed as much energy as possible, so that way the shock absorbers don't then have to take that energy back on rebound.
So like if you hit a pothole or speed bump too fast, and you feel it, and you're like, ooh, that's the part for me.
Yep. So you can imagine we're catching a vehicle, right? And oftentimes we're catching a vehicle several times a second. And when you account for the leverage ratios that these parts see, sometimes 2 or 3 to 1 when you're on the inside of a control arm relative to a wheel, you can see leverage ratios of 2, 3, 4x to 1. So if you've got a 6,000-pound vehicle, 1,500-pound corner weights, you could see 4,500, 5,000 pounds at the bump stop itself. So pretty significant loads put on these relatively small parts. You also see a lot of cycles. Suspension goes through a ton of work while you're using it, right? Especially in an off-road application where you're using the full suspension stroke. And then the last layer of it is the automotive environment is really harsh. You're exposed to oil, you're exposed to moisture, salt spray, temperature variations from negative 20F to the desert, right? It's all over the place. And you really need to be able to hold up to those extreme conditions reliably and repeatably, right? You want the ride feel to also be consistent. So when we first launched this business, we 3D printed our parts using filament. And that was great to get an initial feel for how the parts performed. We were able to iterate really quickly on internal geometries and structures. We could tune those port diameters. We could change fitment, et cetera, right? Tons of benefits, some drawbacks too. So the early prototypes that we made failed pretty reliably. But what's interesting about this failure mode, if you look at it, is yes, there's some failure along the layer lines, which is predominantly the way people think that 3D printed parts fail. They expect delamination between layers. But if you look a little bit more closely, there's also failures against the layer lines, vertically in these parts. That shows us that the material is fatiguing or something else is happening that's causing the material to break down. We found this to happen in high stress locations on the parts, but it really correlated much more heavily with time in field, which means that either something's happening chemically with the material or there's a fatigue failure happening with the material. And that kind of brings us to one of the core fundamental limitations of 3D printing filament. 3D printing filament, by its very nature, you're already printing a recycled polymer. Because in order to make filament, you have to melt the polymer at least once. It put it through the die, pull it, run it onto a spool, and then that's already been melted once before you even put it in your printer in the first place. So by the time you've made a finished part, you've melted the material at least twice, often 3 times. The limitation there is every time you melt a polymer, not only does the screw in the screw extrusion, or in the filament extrusion line, break up that polymer chain, but you also go through polymer scission, or molecular chain scission. So the polymer chains get broken down a little bit, the material loses some of its properties. Particularly with elastomers, you lose a good bit of elongation at break. So that's how much you can stretch that polymer before it finally gives way. And you do lose a good bit of ultimate tensile strength as well. So you can almost think about it as like embrittling your material, right? It gets just a little bit harder to work with and a little bit less durable and tough. This degradation also stacks. So with every subsequent melt cycle, you're compounding that loss. And it's between 5 and 20%, probably closer to 10 to 15 for normal use cases. So fundamentally, filament is flawed in that regard. The other challenge with filament is you're beholden to whatever somebody else decided to turn into filament. There are thousands of grades of TPUs. When people say TPU is just TPU, that's like saying a car is just a car, right? It has 4 wheels, but how many cars are there in the world? And how many different purposes do they all have, right? So with TPUs, there's 2 bulk categories. There's a bunch of nuance here, but generally you can sort TPUs into 2 different grades: esters and ethers. Esters excel at high mechanical loads. They're naturally resistant to oil exposure, but their main drawback is they hydrolyze. This happens with a lot of different polymers, but when exposed to moisture, a lot of polymers will break down and degrade. If you've ever seen a pool noodle that's been used and you can like squeeze it and it all kind of crumbles and breaks apart, that's partially hydrolysis and partially UV exposure. But hydrolysis accomplishes a very similar effect where it just kind of turns into powdery, brittle nothing, right? Ether TPUs don't exhibit hydrolysis, but they do lack mechanical strength. They rot when exposed to oils as well. So you can imagine in an automotive application, especially like in the Northeast, where people undercoat their vehicles with an oil spray, that's a non-starter, right? If you've got these parts that will swell and then immediately they'll break away from their mounting hardware or break off the vehicle, a swollen part or a softer part is not going to work for you. So we have a few features in each of these different grades that we want. What's the option here? The option is a stabilized ester. So there's a chemical compound that you can bake in to TPUs that allows them to be much more resilient to hydrolysis while also preserving all the really beneficial features of an ester-based TPU. So with a stabilized ester, one of the big challenges, though, is it's not available in filament form. And that goes back to the original point of you're stuck with whatever someone else decided to make as filament. And it doesn't exist in filament form. And then finally, compounding. So almost everything that's made from a plastic or a polymer that you interact with, especially if it's injection molded or extruded, any sort of other processing, it's typically been compounded with something. Usually compounding is done to add color to a part, but it can also be done for mechanical or thermal or other reasons. With respect to 3D printing filament, they typically compound solely to add color. And you have to think about the supply chains that we're working with here. They're really catering to hobbyist use. You know, people are printing toys and widgets and gadgets, right? Color is fine. And so they fill it with additives, they add some color, put it on a spool, and they ship it to the person who bought it. 99% of the time, that's great. For our use case, where we're already pushing the limits of what's possible from a product strength category, and we're also really stressing the part, we need as much strength as possible. So looking at a couple of different additive options that can make your part black. Carbon black is the most common option. Carbon black is, think of almost like coal dust, right? It's black, it's made from carbon. It adds UV resistance simply because it's opaque. So UV and light doesn't penetrate through the part, and it colors your parts. Great. Except it reduces your part's flexibility significantly, which on a part like this elastomer damper is really critical. And it just doesn't really add much else to the part. Two other options are graphite and molybdenum. So graphite has super low friction, and as the part wears, as the TPU abrades away, you're exposing more graphite inside the part, basically in suspension in that polymer. It also gives you some creep resistance, and the biggest thing is it has a very minimal impact on part flexibility. So the graphite doesn't really, it's not very stiff or rigid inside that matrix, and it allows the part to flex more reliably. And then, when my computer stays awake, there we go. And then the last one is molybdenum. So molybdenum is often used in greases, also to provide really good friction characteristics, and especially in high pressure applications, molybdenum is great. There's one more benefit to graphite though. Graphite's an excellent thermal conductor. And when we're printing layer by layer, laying down hot layers of polymer, we want the different layers to conduct heat between each other. Because then your currently printing layer, you can dump all the heat from that hot polymer right into the prior layer to A, help set your existing layer, but also to provide a more uniform thermal gradient throughout the part. So the graphite actually provides us a processing aid as well, where we're able to get better interlayer adhesion. We get all these mechanical properties out of the material, and the part's black, which is cool. It helps check some boxes for us. So yeah, the TPUs were used for a while, 20 years ago, 30 years ago, for automotive parts like bushings and other things similar to what we're making. They were injection molded, and they stopped doing it in part because there was hydrolysis. Now and this is all from my sales rep at my polymer supplier. So with the advent of some of these stabilized esters, they're actually starting to push back into the automotive space again because it has mitigated a lot of the issues. But the main downside of a stabilized ester is cost. They're much more expensive because they kind of bridge the gap between the different grades. Any other questions? So just to kind of pull the material story together, going all the way back to filament and its kind of core deficiency. Filament suffers from degraded molecular weight, right? We've melted the material multiple times, we've broken down those polymer chains, they're less effective. On top of that, we also know that we need a slightly different material, right? We're under the right umbrella, we're under the TPU umbrella, that thermoplastic elastomer, but we need different additives, and we need a different base chemistry. And then finally, it's not working as filament, right? So how do we print it? We have to not use filament. And that kind of comes to what our niche is. So our niche is fused granular fabrication, or for some of you that have heard of pellet extrusion in the 3D printing space, that's what this is. Pellet extrusion is 3D printing directly using the injection molding pellets as opposed to from filament. And so we machine in-house a little micro injection molding screw as well as a barrel. And those parts interface with each other to grind, compress, and then extrude injection molding pellets right on our 3D printer's print head. So this whole thing is reciprocating around in the XY plane, the Z-axis is moving down, and we've got a large feed tube coming down with all the pellets in it. This checks a lot of boxes for us. One, we can use the exact same polymers that you would otherwise injection mold or extrude without having to melt them into filament. And it opens up all those opportunities for custom compounding that we talked about prior. So you can do graphite, you can do molybdenum, you can do whatever you want, as long as you can coat the pellets in it and then put it into the print head. I included a little cross section. We're actually passing around the barrel and the screw right now, but you can see we use a zero compression screw, which is a little counterintuitive. A lot of extrusion and injection molding processes use a high compression screw, meaning that the core of the screw tapers outward. We found that we had much more repeatable and reliable results with a zero compression screw. So that root remains the same. And again, you can see kind of how the pellets would come into this barrel. They would be captured by those flutes of the screw and be dragged down. And the hot zone is roughly from here downward. There's a thermal gradient here. And that allows the parts or the material to be compressed, heated, and then extruded reliably inside of the print head. And then the last layer to this is drying and mixing your material. And this is surprisingly more nuanced than it seems. So
Than we thought.
yeah, that's fair.
None of us are majors in material science, so a lot of this took years of trial and error to figure out.
Yep. Yeah. So this machine does a lot of things, and it looks like it does too. So there's a large vacuum on the top that pulls all the pellets into the machine. So that's how you feed. So you can vacuum distribute your raw material into the machine. It holds about 100 and 150 pounds of pellets at one given time. There's a large 5 horsepower motor running right up through the middle, coaxial with the chamber, and that helps to churn and agitate the raw material while it's in the hopper. The reason for that is twofold. One, to provide uniform drying throughout the chamber, and two, to ensure that the graphite is distributed evenly throughout the entire stack. On top of that, the entire thing is heated up to 100 degrees Celsius, so it's a closed loop, closed cycle system. We pull hot air through, there's a PID loop temperature controller that heats it, and then feeds it back through the bottom. And again, this is all being agitated simultaneously, so you get a really good uniform temperature gradient throughout the chamber. And the last thing, and this was the game changer, for the longest time I thought that if you just heated something up with enough hot water, it would be dry. Thank you. Hot air. In reality, you're just pushing hot, moist air through the same loop. So we added a series of molecular sieves into this stack. And what those do is they lower the dew point of that air that's being circulated through the system down to about -40 to -60 C. So pulls the relative humidity down from ambient, which is in that room is about 40% relative humidity, down to between 0.1 and 0.5%. That draws all the moisture out of the granules, dries them out thoroughly. And the important part with that is if you go back to the design of the print head, you can imagine that, call it ambient temperature here, and we're getting progressively hotter throughout. Eventually, at some point, that water inside the pellets is going to flash boil. And that's going to create significant variations in your ability to control flow. So if we can pull all that humidity out of the part and out of the polymer entirely, then we get much more reliable and repeatable results. And those little flash boiling, when the water flash boils inside the barrel, it actually causes a pretty dramatic variation in part cosmetics, part strength, and we've made a lot of bad parts because of that specific issue. So fixing it was really critical. So, we're making 3D printed suspension parts. What does reliability look like? We've been selling these for about 3 years. We've shipped 22,000 parts to date. We have a failure rate of less than 0.1%. With filament, that failure rate was closer to 30%. So pretty dramatic change. Not just due to pellet extrusion, that's due to pellet extrusion, material selection, material compounding, material handling. You put all that together into a cohesive manufacturing story, and that's how you get there. It's not any one individual part, it's the system as a whole. Couple of cool, kind of use cases. So we have a bread and butter product, but we've had a couple of cool opportunities to work with people that are kind of pushing the limits of what you can do, and they've trusted us to try some of this stuff. So we're actually an OEM supplier for a company called Annex Suspension. They make suspension parts for track cars. They had a cast urethane bushing in their coilover stack. So cast urethane was a 2-part. You mix them, they set, and predominantly people think that cast urethanes are always going to be better than a 3D printed part because 3D printed parts have layers. Their part was failing in the field reliably due to compression set. And so the parts you can see here on the left, that's after being loaded up with, I think we tested at 3,000 pounds sustained for 24 hours at 25 C. So ambient temperature, like a little over a ton. Pretty standard for what you could see for the corner of a vehicle. Theirs were all taking a set, and then there would be play in that stack. So we printed a series of prototypes for them. We ran them on the suspension dyno, and we're now a OEM supplier for them for their line of coilovers. So they make their parts, they use our bushings in their assembly, and they've been very happy with the parts. And we saw a 66% reduction in compression set. So they held up much better. And then this one was for a theme park company that asked not to be named, but I could share the part. So this one was a custom spring that they needed. They park a whole roller coaster on top of this part. They need a tailored spring within a certain aspect ratio and packaging. So it had to be short. It's, what, 20 millimeters tall, give or take? So it's pretty short, and it's pretty large in diameter. You can imagine a coil spring doesn't really fit into that aspect ratio. And it needed to be 174,000 pounds per inch. So this is loaded with 18,000 pounds about 1,000 times a day. So, you know, we put it through a good bit of longevity testing to validate. And we actually just shipped that short production run on Monday. And we were able to hit roughly a 5% tolerance band for the stiffness. And of course, because they're 3D printed, you can tailor the geometry and the fitment to whatever you need, right? So we've got a low retention lip and a couple of through-bolt holes. Makes it really clean to mount into their solution. And again, all these applications are really only possible by being able to print from materials that are otherwise not available for printing. And I kind of alluded to it a little bit, but I just kind of wanted to highlight this. This wasn't easy. We had a plethora of additional hurdles from material integrity. You know, I alluded to drying them properly, but also how much graphite are you going to compound with the material? How do you ensure you reach a saturation point or you uniformly distribute it, right? What's your graphite supplier? What's the particle size? All those sorts of things. Machine optimization. I didn't show you guys the motion system that the machines use. We use an off-the-shelf motion system, and we just heavily retrofit a turnkey printer. But choosing the right printer was really important. You can imagine a lot of our firmware and our control over flow is very different from a traditional filament printer. And then quality and aesthetics. So especially for our direct-to-consumer products, you know, we're printing with this extrusion print head, screw extrusion print head, which inherently has a little bit less control over volumetric flow. You think about with filament, you're pushing a cylinder through a tube. If you know the diameter of that cylinder and you know the axial length of the cylinder that you've translated, you've got a volume, and that's very clean and very fixed. With this, we're turning a screw in a material that's the consistency of honey, and we're pushing it through a nozzle at varying speeds. It's really challenging to get that right. And so that subsequently trickles into what the parts look like. And getting that to look good, getting it to be a good turnkey consumer product took a lot, but I think we're there. So, yeah. That's it. Any questions for us? Yeah.
Do you have plans to sell your extruder design or material processing setup to other companies?
Yeah, so we've gotten a lot of requests for the print head itself. And the hurdle there is supporting it. My concern is that if we end up going mass market with that, you end up with a bunch of people trying to retrofit it onto printers that either can't accept it because they don't have a rigid enough motion system to move a relatively heavy print head, or they don't have the ability to tune, or they underestimate the difficulty to tune it in. It isn't easy, it is doable, and we've processed a wide range of materials. I like to tell some of our clients, if you can injection mold it, we can print it, and that's generally true. It's a good rule of thumb. So the short answer is we would love to, and we're trying to figure out the right